Alright guys, today we're going to go over note card 24, and this is called implicit differentiation. Now, before we get started with this, let's talk about functions real quick. Alright, most of the functions we see are usually written like this, like f of x equals 3x plus 5, or y equals 3x plus 5. And then if we were to graph that, it would have a y-intercept of 5, and then we rise 3 and run 1. And we keep doing that, and we get our line in this case. This is a function, okay? It's a function because for any value of x, it passes the vertical line test. All right, well, what about if we don't actually have a function? Okay, we're used to functions that are explicit, okay, which means that y equals something in terms of x. All right, we're not used to things that look like this, which we call implicit relations, when the x's and y's are together. Okay, so that would be an implicit relation. Now this might be a function, it might not, okay? So we have a special way how to take derivatives of this thing. And that special way to take derivatives, this might not be a function, but it still has a derivative. So we use a process called implicit differentiation to be able to take derivatives of things that might not be functions. Okay. So what Stacy McMullen tells us, it says to find the derivative for an implicitly defined relation, differentiate both sides with respect to x, collect all the dy over dx terms on one side, and move all the other terms to the other side, factor out the dy dx, and then solve for it. So the best way to do this is just by working through several examples on this note card. So I'll show you how to do it. Now it might take a little bit more space, so I'm going to do it on notebook paper. All right. So here's problem 1. Problem 1 says, find the derivative dy dx for this implicit relation, y to the 4th plus x cubed times y to the 5th minus 2x to the 7th equals 13. All right, so it's a whole bunch of pluses and minuses, so I'm going to take the derivative of each piece. Now, let's look at this first piece. What's the derivative of something to the 4th, some variable to the 4th? Well, the 4 would come down. We would reduce the power by 1, so we would have y to the 3rd. But we also, this is like a chain rule, we have to multiply times a dy over dx. Okay, so that would be the derivative of the first term. Now, on the next term, if you notice the next term, we have a product. Okay. So I have to use the product rule. Derivative of the first term is 3x squared. Okay, but now I'm taking a derivative of x with respect to x. So that's the entire derivative of the first term times the second term plus the first term, x cubed, times the derivative of y to the 5th. So we would have 5y to the 4th times dy dx. Now the next term, what's the derivative of that? It's negative 14x to the 6th, and we're taking derivatives with respect to x. And then the derivative of any constant is always 0. Okay, so I know that's kind of hard to see. All right. Now, a couple things we don't really need to put here. Whenever you take derivatives of x terms, since there's an x on the bottom, you really don't need this dx over dx piece, because anything over itself is really just 1. So anywhere I see a dx over dx, I'm just going to cross it out. We don't really need to put that. But when you take derivatives of y terms, you need to put this dy over dx as part of it. So I'm just going to rewrite this. I have 4y cubed times dy over dx plus 3x squared times y to the fifth plus, okay, if I just rearrange some of this stuff, I can move the coefficient out front, so that's 5, and then x cubed, y to the fourth, dy dx. Then minus 14x to the sixth equals 0. Now, two of these terms, this term right here and this term right here, have a dy dx on it. These other two terms do not have any dy dx's on them. So I want to move these two terms that I underlined in green over to the other side. Okay? So if I want to do that, I would have to subtract 3x squared y to the fifth from both sides to get that to cancel out. Then I would have to add in 14x to the sixth on both sides to get rid of that term. So after I do that, I have 4y cubed dy dx plus a 5x cubed y to the fourth dy over dx equals, I have these two things now. I have a negative 3x squared y to the fifth and a positive 14x to the sixth. Now, since both of these terms have a dy over dx on them, I'm going to factor that out. So I'm going to factor out a dy dx, and if I do that, I have 4y cubed plus 5x cubed y to the fourth. It's going to equal negative 3x squared y to the fifth plus 14x to the sixth. Now the goal is to get dy over dx by itself. So I need to divide by that parenthesis. So if I do it on one side, I have to do it on the other side. 4y cubed plus 5x cubed y to the fourth. So this right here is actually the derivative. And that right there is the derivative. And if you wanted to make it look a little bit nicer, look at these two terms. What do they have in common? Well, they have an x squared in common. Okay, then I'd have negative 3y to the fifth left there, and I'd have plus 14x to the fourth. And out of these two terms, they have y to the third in common. Then I have 4 plus 5x cubed, and I'd have a y left. So I could write it a little bit nicer like this. Either way, both are equivalent to each other. So the derivatives can kind of start to look nasty when you do implicit differentiation. All right. Now, why did we have to take implicit differentiation here? I'm going to actually let you take a look at what this original implicit relation looks like. Now, we can't do this on the graphing calculator because the graphing calculator wants functions. Okay? But if we use an online graphing app, this one's called Desmos. Okay, you might have seen this before. I'm just going to type that in. So, y to the fourth plus x cubed y to the fifth minus 2x to the seventh equals 13. Okay. As you can see, that's definitely not a function. Okay, that's definitely not a function. Our graphing calculator will not do that. Okay. All right, now let's try the next problem. Number 2 here, it says find the line of tangency. So I want the equation of the tangent line to this curve, and it might not be a function, but it's still a curve, at this point. Okay. So as I go through my problem, if I want to find the equation of the tangent line, I need two things. I need a point, okay, and I need a slope. So the point, they actually gave me both the x and the y value of the point, -1, 2. But I don't know what the slope is. So the slope is going to be equal to the derivative evaluated at that point. Now normally we just need the x values for explicitly defined relations, but for these I'm actually going to need both the x and the y values. So I'm going to show you how, and the relation here was x squared minus xy plus y squared equals 7. Okay. So before I find the derivative at that point, I have to find the derivative for all x and y values. Okay. And before we actually do that, let me jump onto Desmos so you can see what that looks like. Okay, let's take a look at what that relation looks like. So x squared minus xy plus y squared equals 7. So what they want to know is, at the point -1, 2, okay, so at this point right here, at that point right there, if I drew in a tangent line, what would its equation be? If I drew in a tangent line right there. That's what the question's asking me to find. Notice that this is not a function. Our graphing calculator won't do it for us. Okay. So I have to take the derivative of this so I can figure out this right here. So the derivative of x squared is 2x. You could put the dx over dx if you want to. I'm not going to. All right, now this thing right here is a product, so I have to use product rule. So what's the derivative of -x? Well, it's -1 times the second, which is y. All right, plus the first term, which would be -x, times the derivative of y. Well, the derivative of 1y is just 1. But whenever I see a y and I take a derivative, I need to put a dy over dx in it. All right. Now I take the derivative of that. Derivative of y squared is just 2y. But again, I'm taking a derivative with respect to y, so I need to put in a dy over dx. Now I do the derivative of this, which is just 0. Derivative of a constant is 0. So when I rewrite this, I have 2x minus 1y. All right, this is -x times 1. That's -1x with a dy over dx. Then I have a plus 2y with a dy over dx equals 0. So let's move these two things that do not have a dy over dx, to the other side. So let's subtract 2x from both sides to get that to cancel. Then let's add a 1y to both sides to get those to cancel. Okay. And 0, and then we have all this other stuff, so it doesn't really matter. So now I have a -1x dy over dx plus a 2y dy over dx equals negative 2x plus 1y. Okay. Now I'm going to factor out the dy over dx. I'm going to get negative 1x plus 2y. The right side's going to stay the same. The goal is to get dy over dx by itself. So I need to divide both sides by negative 1x plus 2y. Okay. So the derivative relation is negative 2x plus 1y. I can just write plus y. Over negative 1x, I can just write that as negative x plus 2y. So this is the derivative. That's the derivative relation. But I only care about the slope, the derivative at a single point. And that point has an x value of negative 1 and a y value of 2. So now, to figure out the derivative at the point negative 1, 2, all I'm going to do there is everywhere I see an x, I'm going to plug in negative 1. Everywhere I see a y, I'm going to plug in 2. So negative 2 times negative 1, just kind of plugging and chugging here, plus the y value of 2 equals negative 1, okay, plus 2 times 2. I'll just simplify correctly. Negative 2 times negative 1 is positive 2, plus another 2 is 4. Okay. Negative times negative 1 is positive 1. 2 times 2 is 4. 1 plus 4 is 5. So I just figured out the slope of the tangent line would have a slope of 4/5. So I can come back up to the top, and I know the slope now is 4/5. So if I wanted to write the equation of the tangent line, it would be y minus 2 equals 4/5 x minus negative 1. And two negatives here are a plus. This is the equation of the tangent line. Okay. So let me go back to Desmos really quick, and I'll show you what the tangent line looks like. Okay. So I think the equation of the tangent line is y minus 2. It's really nice with Desmos because you can type it in point slope form. It's 4/5 x plus 1. Okay, there we go. Notice it hits right there. It hits the point that we care about. And then it looks like it's hitting once, and that looks like the instantaneous rate of change. It looks like the instantaneous rate of change right there is 4/5 at that point. So Desmos can be nice for us. So let's do problem 3. It says, find the instantaneous rate of change. What does that mean? That means slope or derivative at the point 1, 1. All right, so what I'm trying to find is I'm trying to find the derivative evaluated at 1, 1. So how do I do that? This is an implicit relation, so I have to use implicit differentiation. Derivative of x would simply be 1 plus, looks like the next term has a product, so I got to use product rule. So the derivative of the first would just be 3 times the second, which is y. I don't need a dy dx because I took derivatives of the first term there. All right, plus the first term, 3x, times the derivative of y. Derivative of 1y is just 1, but I need to put a dy dx on it. Okay. Now the derivative of negative 2y squared would be negative 4y, but I just took a derivative of a y term, so I need to put on a dy dx. The derivative of a constant is 0. So these two terms do not have a dy dx. So I could subtract 1 and I could subtract 3y from both sides. So now we do have dy over dx on the other two terms. Let's just factor that out. So if I factor it out, I would get, well, 3x times 1 is just 3x. And I have a negative 4y. So that would be the left side, factored out at dy dx. Okay, and on the right side, we just have negative 1 minus 3y left. To get the dy over dx by itself, I'm going to divide by 3x minus 4y. Okay, so this is the derivative for all points on the curve. We care about it only at the point 1, 1. So everywhere I see an x, I'm going to plug in 1. Everywhere I see a y, I'm going to plug in 1. So I'm going to have negative 1 minus 3 times 1 over 3 times 1 minus 4 times 1. Okay, if we do some simplifying there, negative 3 times 1 is negative 3. Negative 1 minus 3 is negative 4. 3 times 1 is 3. 4 times 1 is 4. 3 minus 4 is negative 1. And negative 4 divided by negative 1 is positive 4. That's my answer there. The slope there would be 4. The slope at this point, the slope of the tangent line, would equal 4. Let's go to question 4. So they give me a relation, x squared plus y squared equals 25. And you might be remembering this from pre-calculus or algebra 2. This is actually the equation of a circle. And 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This is a circle centered at the origin with a radius of 5. That's what, well, it's not a function, it's a relation. Okay. What they're asking me to find here, they want to know what the second derivative is at the point 4, 3. Okay. So 4, 3 is a point on the graph. Here's the point 4, 3. They want to know right there what's the value of the second derivative. Okay. So let's figure out what the first derivative is first. Okay. So here's my relation. X squared plus y squared equals 25. Take derivatives. Derivative of x squared, simply 2x. Okay. Derivative of y squared would be 2y, but I have to put on a dy over dx. Derivative of a constant is 0. So I could subtract 2x from both sides. And then to solve for dy over dx, I can divide both sides by 2y. So the equation of the first derivative, 2 over 2, simplifies. It is basically negative 1x over y. So that right there is the equation of the first derivative. Now, how do you get to the second derivative? Well, let's take the derivative of this. This is a first derivative. And if I take another derivative of all this, that would get me to the next derivative. So that would be d squared y over dx squared. Now, what do you notice about this side? This side right here is a quotient. Okay, so you can use quotient rule, or you could write it as a product. Either one. I'm just going to leave it as a quotient. So if I use quotient rule, we say low y, derivative of high, So the derivative of negative 1x is negative 1 minus high derivative of the low. So the derivative of 1y is just 1, but we need to make sure we put in that dy over dx. All over low squared. Okay, so y times negative 1 is negative y. Okay. You have a negative times another negative, that would be positive. So plus x times 1 is still x times dy over dx all over y squared. But we can do something else here. We can make one more substitution, and you might already know what it is. We already have an equation for dy dx. It's right here. So I can plug in a negative x over y. So if you want to think about this, we would have a negative y plus, well, x times negative x would be negative x squared. So I can say minus x squared over y all over y squared. So this is an expression for the second derivative, but we want to know what is the value of the second derivative at the point 4, 3. So everywhere I see an x, and here, I'm going to plug in a 4. Everywhere I see a y, I'm going to plug in a 3. So this says negative y, so negative 3, okay, minus x squared, 4 squared is 16, over y, which again is 3. So this is like negative 3 over 1 minus 16 thirds, all over 3 squared. Okay, and we just have to simplify it. All right. So if I'm going to simplify this, I need to get a common denominator there. So I need to multiply by 3 over 3. So now I have negative 9 over 3 minus 16 over 3, and 3 squared is 9. So negative 9 minus 16 is negative 25. So I have negative 25 over 3. I'm going to divide it by 9. Okay. If you remember your keep, change, flip, that's going to be the same thing as saying negative 25 thirds times 1/9. To get a final answer here of negative 25 over 27. And that's my answer. Negative 25 over 27. Now there's another way you could have done this. You could have actually figured out what dy dx was at 4 thirds. Okay. So if I were to plug in 4 there and 3 there, that would just be negative 4 thirds. Okay. And then once you found that, when you started plugging numbers in here, you could have plugged negative 4 thirds in for this thing when you were calculating over here. You could have done that. So we got more examples on the back that we'll go through together. All right. So on the back it says find y prime. So they're asking me for the derivative. I guess a better way to say that is to find dy over dx. So here's number 1 on the back. Tells me negative 4 equals y cubed plus y squared minus 5y minus x squared. So as I start taking derivatives, I just take one piece at a time. Derivative of a constant is 0. Derivative of y cubed would be 3y squared, but I need to remember the dy over dx. Derivative of y squared would be 2y with a dy over dx. The derivative of negative 5y would be negative 5 with a dy dx on it. Then the derivative of negative x squared is simply negative 2x. You don't need the dy over dx on that one because it's just x. Okay. So we could add 2x to both sides. And then we could factor out. I've added 2x to that side, I've added 2x to that side, so those go away. I could factor out the dy over dx. Then I have 3y squared plus 2y minus 5. Then to get dy over dx by itself, I would divide both sides by that parenthesis. 3y squared plus 2y minus 5. And this right here is the derivative function, or not function, derivative relation. So you could stop there. Number 2. So it's 2y equals x squared plus the sine of y. Just take the derivative of each piece, nice and slow. Derivative of 2y would be 2 times dy over dx. Derivative of x squared is simply 2x. Now the derivative of this thing is a chain rule. So the derivative of sine of anything is cosine of whatever's inside times the derivative of the inside. Well, the derivative of y would just be 1, but since it's got a y on it and you take a derivative, you need a dy over dx. Let me move, so let's rewrite it real quick. 2 dy over dx equals 2x plus the cosine of y times 1 doesn't matter, times dy over dx. These two terms have dy dx's on them, so we want to get those on the same side. So I'm going to subtract the cosine of y dy over dx from both sides. So now I have 2 dy dx minus the cosine of y dy over dx, and that's going to equal 2x. So just like before, factor out the dy over dx. And if we want to solve for dy over dx, we would just divide through by 2 minus the cosine of y. So this would be the derivative relation. All right, number 3 here, it says find the equation to the tangent line at this point. So I already know the point. The point is 1, negative 1. But to figure out the slope, that would be the derivative at that point. Okay. So we don't know that part of it yet. So before I can find the derivative at a point, I have to find the derivative of the relation. So, all right, this is some sort of parabola. All right, so there is my relation. Notice, got to take the derivative of that, but there's a product right there. So I got to use product rule. All right, so here it is again, x times y squared equals 1. There's the first term, there's the second term. So product rule, derivative of the first, which would be 1, times the second, y squared, plus the first times the derivative of the second. So that would be a 2y, but we need to put in a dy dx. That's going to equal the derivative of the constant, which is just 0. Okay, so let's solve for dy over dx. So let's subtract 1y squared from both sides, which is just y squared. So now I have x times 2y is 2xy times dy over dx equals 0 minus y squared is negative y squared, or negative 1y squared. If I want to solve for dy over dx, I have to divide both sides by 2xy. Okay. So this is the derivative equation. Let's think about what this means. This means negative 1 times y over 2xy. One of the y's cancel. It's kind of nice. So that equals negative 1y over 2x. Now let's figure out what the derivative is at the point 1, negative 1. So everywhere I see an x, I'm going to plug in 1. Everywhere I see a y, I'm going to plug in negative 1. So negative 1 times the y value, which is negative 1, over 2 times the x value, which is 1. Negative 1 times negative 1 is positive 1. 2 times 1 is 2. So I just figured out the slope there is 1/2. Once I know that, I can write the equation of the tangent line. That would be y minus negative 1 equals 1/2 x minus 1 in point slope form. So there's my answer. We can use a tool like Desmos to check ourselves out a little bit. So here was the relation xy squared equals 1. Oh, I thought it was a parabola. It's not. It's something else. Okay. And let's, at the point here, 1, negative 1 is right there. So I want to draw in a tangent line right there. Here's the equation of the tangent line that we got. Y plus 1 equals 1/2 x minus 1. There we go. Does it look like it hits that 1, negative 1? Yep. Does it look like it just hits this curve in green at that one spot? All right, I know it hits again over here, but we're just looking at things that are close to that value. It only looks like it's hitting in that one point. If I zoom in to that point right there, looks like it's just hitting there. You can zoom in as close as you want. Okay, it's hitting right there. That whole idea of local linearity. All right, now number 4, don't really know how to do that one yet, so that's okay. All right, so, all right, it says find the derivative for natural log of xy equals e to the 2x. You guys don't know how to calculate the derivatives of natural logs yet, or e, so I'm going to help you out with this one. So whenever I have a natural log, okay, the way I'm going to figure that out, all right, so to calculate the derivative of any natural log, you're going to take the derivative of the inside, okay, so we're just going to write that. Okay, I'm going to take the derivative of the inside over just the inside equals, calculate the derivative of e to the 2x. Well, it stays itself, so e to the 2x times the derivative of the exponent. So what's the derivative of just 2x? It's just 2. Okay, so that's that derivative. Now, let's just kind of do some side work. What would the derivative of xy be? Well, that's a product, so I have to use the product rule. The derivative of the first term's x, derivative of that is 1, times the second, plus the first, times the derivative of the second. So the derivative of y would just be 1, but we need to put a dy dx on it. Okay, so I can substitute this stuff right in for all of this. All right. at the same time, to get rid of this xy, let's go ahead and multiply both sides by xy. And that gets those to cancel. So if I put this stuff in, okay, 1 times y is y. X times 1 is x, so plus x, but it's got a dy dx on it. That's going to equal this right side. I can move the 2 out front. So 2e to the 2x times y. Now, my goal was to get dy over dx by itself. So I could subtract y from both sides. That would eliminate that. Then I can divide through by x. And that gets that to cancel out. So here is actually the derivative of that. Try a few more. Find the instantaneous rate of change. What does that mean? That means derivative, but evaluated at the point 1, 1. So let's take the derivative of each piece, derivative of x squared 2x, plus this next term is a product, so I got to use product rule. So the derivative of 2x is 2 times the second term of y, plus the first term of 2x times the derivative of 1y, which is 1 times a dy dx. All right, plus the derivative of this thing, which would be 2y times dy over dx, equals the derivative of that thing is 0. Now, where are you going to make your mistake? You're going to forget to take the derivative of a constant. You're going to write 4 there. So that would be a common mistake. Okay, let's get rid of these 2 terms, move them to the other side. So let's subtract 2x and let's subtract 2y from both sides to get those to cancel out. Let's factor out the dy over dx. So if I factor that out, this thing would be 2x plus this thing is 2y. Subtract these. So here is actually, if I factor out a negative from here, it would just be x plus y. Now I can divide both sides by 2x plus 2y. And you can again do some factoring here. Factor out a 2 there and you get an x plus y again. Something kind of cool happens here. Those x plus y's cancel out and you're left with negative 2 over 2, which is just negative 1. Okay. So here the derivative is a constant. It's negative 1. So that means that the derivative evaluated at the point 1, 1, there's nothing to plug in, so you can just leave it as negative 1. There's no x and y values in it. All right, let's check that one real quick. So here's my original function, x squared, not function, but relation, plus 2xy plus y squared. Oops. Equals 4. Okay, now I don't see anything. Why don't I see anything? Because I'm zoomed in. So there we go. So what does that actually give us? It looks like a set of parallel lines. Okay, it looks like a set of parallel lines. If I keep zooming out forever. So think about the point 1, 1. Okay. Come into it a little bit. Here we go. The point 1, 1 is right there. Close to it. 1, 1. We found that the derivative slope was -1. Doesn't it look like if I drew in a tangent line here, wouldn't it have a slope of -1? Doesn't it look like I'm going from that point to that point, going down 2 and right 2? -2 over 2 just equals -1. So at this point, the slope there is -1. So that's why the math that I showed here works out to just be a constant. All right. Let's look at this next problem. Okay. Now, there's multiple ways to do this problem. Okay. It's kind of up to you how you want to do it. To me, it seems like an easier way to go about this problem. Okay. An easier way to go about this problem would be to just go ahead and multiply both sides by x plus 1 right away. And then that cancels that out. And what do you have left? You have x minus 1 equals, what happens when you distribute that out? Well, you get xy squared plus y squared. Why do all that? Because it'll be easier to take the derivative. Okay, so I'm going to go from this point. All right. So what's the derivative of x? It's 1 minus, what's the derivative of a constant? It's 0. Now next term, it's a product, so I got to use product rule. Derivative of the first term would be 1 times the second term. All right, plus the first term, x, times the derivative of y squared, which would be 2y dy dx. Plus the derivative of that term, that would also be 2y dy dx. So I have 1 equals y squared plus 2xy dy dx plus 2y dy dx. Subtract y squared from both sides. Okay, so I have 1 minus y squared. Okay. Basically subtracting out y squared from both sides. That gets those to cancel. Factor out a dy dx. And I have 2xy plus 2y. That would be dividing by all that. 2xy plus 2y. So if you do a little bit of factoring here, 1 minus y squared can be factored into 1 minus y times 1 plus y. And on the bottom, you could factor out a 2y. And you get a x plus 1. But that doesn't really help. I can't cancel anything else. So either way you want to do it, you can leave it like that as the answer, or you can write it like this. All right, 2 more problems here. It says find the derivative for this thing. So let's just take one piece at a time. Derivative of x is 1. Plus, okay, the derivative of this requires the chain rule. So tangent is the outside function. So the derivative of tangent is secant squared of whatever's inside times the derivative, or I should just say the derivative of xy. Okay. Equals the derivative of a constant is still a constant. So here we have 1 plus secant squared of xy. Now what's the derivative of this product? Well, you got to use product rule. So times derivative of x is 1 times the second, which is y, plus the first x times the derivative of y, which would just be 1, but we need to put in the dy dx. Now this thing needs to be distributed to both of those things. Okay. I could subtract 1 from both sides right away if I want to make the problem a little bit nicer. Okay. So if I distribute that out, I get 1y times the secant squared of xy. I'm just distributing, but I'm putting the 1y first. X times 1 is x, so this would be plus x secant squared of xy, but it's also got a dy over dx. And 0 minus 1 is negative 1. Now this is the only term with a dy over dx on it. So I should subtract out this 1y secant squared of xy on it. So let's subtract out 1y secant squared of xy. So I'm down to that. Let's now divide both sides by x times the secant squared of xy. X times the secant squared of xy. And that gets those to divide and cancel out to 1. And here is the answer to my derivative. Okay. Last problem here. Find the second derivative. Okay. So first derivative, 2x plus 2y dy dx equals 0. That's the first derivative. Okay. Subtract 2x from both sides. Okay. Divide through by 2y. So dy over dx. Okay. 2's can cancel. It's just negative x over y. Okay, second derivative, if I take the derivative of that, it's the second derivative. Okay. All right, if I take the derivative of this, just like before, same as before, got to use quotient rule. So low, d high, minus high, d low. The derivative of y is just dy over dx all over low squared. Okay. But I know that dy over dx is equal to this thing, so I can substitute. Okay, so I get negative y plus x, two negatives, but I need to multiply that times another negative x over y squared. I can write it like negative y minus x squared over y all over y squared. Or you could get common denominators and you can make that look a little bit nicer. Okay, what do I mean by that? I mean, I could get negative y squared minus x squared. Actually, I'm sorry. Yeah, negative y squared minus x squared over y all over y squared. And, or you could write it as negative y squared minus x squared over y cubed. Any one of those three answers would be fine. Okay. But it's also fine to leave the answer like this if you'd rather just leave it like that. I'm okay with that. So they're asking for the second derivative. That's the equation for the second derivative. Any one of these four. Okay. Just make sure you resubstitute that dy over dx in right there. So your packet tonight, the first part, you have several problems where you have to use implicit differentiation. Then you got to find some second derivatives. Okay, and then you have some curve. You're asked to find the derivative, evaluate that derivative at a point, write the equation for the tangent line. So just practicing what we did today. Then you got a form your free response problem, okay, for 1987. All right, and then you got some multiple choice problems, okay, using implicit differentiation. Remember, even though these are multiple choice, don't just circle an answer, show your work for them. Okay, and if you have to use the back, you can use the back. There's room on the back. All right, so that's all I have. Thanks for watching today.